Half the normal matter in the cosmos is simply gone. For decades, this was astronomy's most baffling case, the missing baryon problem. The very atoms that build stars, planets, and even us were unaccounted for in the cosmic ledger. Solving this mystery is crucial because without knowing where this ordinary matter hides, our entire picture of cosmic evolution is incomplete. By the end of this journey, you will understand exactly how scientists traced this vanished material and illuminated the invisible architecture of the universe. We will explore why this matter became invisible to our eyes and uncover the first clues that pointed to its grand disappearance. How much of the universe do you think remains hidden in plain sight? The cosmic ledger, it turns out, was deeply in the red. Picture a meticulous accountant, one who has just received the ultimate balance sheet from the Big Bang itself. This record, imprinted on the ancient light of the cosmic microwave background, tells us precisely how much ordinary matter, the stuff of atoms called baryons, the universe started with. The numbers are clear and unforgiving, yet when scientists began counting all the matter, they could actually see the glittering stars, the vast galaxies, the swirling clouds of gas. The totals came up shockingly short. They could only account for about half of what the cosmic birth certificate promised. This was not a minor accounting error or a misplaced decimal point. It was a fundamental flaw in our inventory of existence, a deficit so vast it threatened to unravel our understanding of cosmic evolution. This glaring mismatch became the driving mystery of modern astronomy, a puzzle officially dubbed the missing baryon problem. If half of the normal matter in the universe was not in the places we expected, the only logical conclusion was that it had to be hiding somewhere in the immense, dark spaces between the stars. So where do you hide half the universe's ordinary matter? The answer lies in the most desolate, empty places we know, the unimaginably vast tracts of space between galaxies. This cosmic wilderness, known as the intergalactic medium, became the prime suspect. Far from being a true vacuum, this space is filled with an incredibly thin, diffuse gas. Think of it not as an empty desert, but as a ghostly ocean, a sea of matter so spread out that a single atom might occupy a space the size of a suitcase. The sheer volume of this intergalactic territory is staggering. If you could gather up all the matter from every star and galaxy, it would fill only a tiny fraction of the cosmos. The rest of space, this immense intergalactic medium, offers more than enough room to conceal billions of suns worth of missing atoms. But there is a catch, a reason this matter has remained hidden for so long. This gas is not just diffuse, it is unimaginably hot, heated to temperatures of millions of degrees by the violent forces of the universe's large-scale structure. At such extreme heat, the gas becomes a seething plasma, a state of matter where atoms are torn apart into their constituent particles. This superheated plasma does not glow in the way a star does. It does not emit the visible light our eyes and traditional telescopes are built to see. Trying to spot it is like trying to see a cloud of steam in a completely dark room. Your eyes are simply not equipped to perceive it, even though you know it is there. Its invisibility is a direct result of its physical state, a perfect camouflage against our primary methods of observation. This fundamental property, its searing temperature, is what made the intergalactic medium the perfect hiding place, turning the missing matter into a ghost that haunts the spaces between everything we see. This superheated state is the key to its perfect invisibility. At temperatures reaching millions of degrees, the gas undergoes a fundamental transformation. It becomes fully ionized, a scientific term meaning the violent heat tears the atoms apart. Each atom is ripped into its constituent pieces, with negatively charged electrons being stripped away from the positively charged atomic nuclei. What remains is not a gas of familiar atoms, but a seething, chaotic soup of free-floating particles known as a plasma. This ionized plasma behaves entirely differently from cooler gases. It does not absorb or emit light in the visible spectrum our eyes can perceive. You cannot see it for the same reason you cannot see the air in a room, but amplified to an extreme degree. Instead, this incredibly hot material glows only faintly in high-energy X-rays. Think of it as a secret message written in ultraviolet ink. Held under normal light, the page appears blank. But shine the right kind of blacklight, and the hidden writing leaps into view. For astronomers, Earth's atmosphere acts like that normal room light, completely blocking the X-ray blacklight from space. This simple fact created an immense observational wall. For decades, our primary window on the universe was optical light, trapping us in a sensory prison where half of reality remained cloaked. To finally read the universe's hidden message, we needed to leave our planet behind and develop a new sense, one capable of seeing the unseeable. To pierce this veil of invisibility, astronomers turned to nature's own lighthouses, quasars. These are not mere stars, but the blazing cores of galaxies located impossibly far away, where a supermassive black hole feasts on surrounding matter. The process unleashes a torrent of energy, making a single quasar outshine its entire host galaxy. Its light a brilliant beacon that journeys for billions of years across the cosmos before finally reaching our telescopes. This journey is the key. As the quasar's pristine light travels through the vast, supposedly empty intergalactic medium, it does not pass through unscathed. It encounters that diffuse, superheated gas. Scientists capture this ancient light and break it down into a rainbow of colors using a technique called spectroscopy. This rainbow is not a smooth blend, however. It is etched with fine, dark lines like a unique barcode. Each of these absorption lines is a telltale fingerprint. Specific elements in the hot intergalactic gas, such as oxygen and hydrogen, are tuned to absorb very specific colors or wavelengths of the quasar's light. By reading this barcode of missing light, astronomers can deduce not just what the invisible gas is made of, but also its temperature, its density, and even its motion. This was the first concrete evidence, the forensic proof that the spaces between galaxies were not a void. They were filled with a complex, wispy web of gaseous structures, a hidden architecture holding the cosmos together. While this method brilliantly revealed the ghostly presence of the gas, it was still an indirect observation, like studying a fossilized footprint. To truly confirm the identity of the missing matter, scientists needed a way to see the ghost itself, to detect the energy it was emitting. But reading the barcode of quasar light was just the beginning. A second, even more subtle method was needed to truly confirm the ghost's presence. This technique relies on the oldest light in existence, the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang itself, a fossilized echo that fills every corner of the cosmos. As this ancient light travels for billions of years on its journey to our telescopes, it does not travel through a perfect void. It occasionally passes through the very clouds of hot, invisible electrons that make up the intergalactic medium and the vast halos around galaxy clusters. When a photon from the cosmic microwave background encounters one of these high-energy electrons, a tiny but crucial transaction occurs. The electron gives the photon a slight boost, a kick of extra energy. This interaction leaves a distinct, minuscule fingerprint on the background radiation, a specific type of distortion known as the Sunyaev-Zeldovich effect. Imagine you are looking through a frosted glass window. You cannot see the glass itself, but you know it is there because the world outside appears slightly blurred and distorted. The Sunyaev-Zeldovich effect works in a similar way. By carefully mapping these tiny imperfections in the cosmic microwave background, astronomers can detect the invisible presence of the hot gas. The gas itself remains completely dark, but its shadow, its effect on the most ancient light we can see, gives it away. This powerful tool acts like a cosmic scale, allowing scientists to literally weigh the invisible mass residing in the largest structures in the universe. It confirmed that these vast reservoirs of hot gas were not just a wispy suggestion. They were real, massive, and contained enough ordinary matter to finally solve the missing baryon problem. The sheer scale of these observations pointed toward a final, monumental task: the need to map this hidden cosmic ocean in its entirety. These observations revealed a hidden architecture far grander than anyone had anticipated. The universe is not simply a collection of isolated galaxies floating in a void. It is structured as a cosmic web, an immense, interconnected network spanning billions of light years. Picture a sponge, but on the largest scale imaginable. Dense clusters of galaxies form the thick knots of this sponge, while long, delicate threads known as filaments stretch between them, connecting everything in a vast, three-dimensional lattice. In between these strands lie the cosmic voids, unimaginably vast regions of near-nothingness, the true deserts of space. This entire structure is woven together by an invisible skeleton of dark matter, whose gravity guides the flow of all normal matter. And it is within these gossamer filaments that the final pieces of the missing matter puzzle were found. This specific environment has a name: the warm-hot intergalactic medium, or WHIM for short. It is a poetic name for an extraordinarily harsh place. The gas here is not just hot, it is heated to a staggering range of 100,000 to 10 million degrees. How does it get so incredibly hot? The answer lies in the relentless pull of gravity. As vast rivers of matter flow along these cosmic highways, funneled by the dark matter's grip, they do not move smoothly. They collide and create immense shock waves like sonic booms on a cosmic scale. This violent process pumps enormous energy into the gas, superheating it and turning it into the diffuse, ionized plasma that has eluded us for so long. Think of a spider's web. The junctions where the threads meet are like the dense galaxy clusters, obvious and easy to spot. But the sticky strands that connect them, the filaments, are far more extensive, crisscrossing the entire structure. It is within this vast, sticky network of filaments that a huge portion of the universe's ordinary matter has been hiding, not in the bright cities of galaxies, but along the dark, intergalactic freeways that link them together. These galaxy clusters are the grand cities of the cosmos. Each one is a metropolis of hundreds or even thousands of galaxies, all bound together by the immense pull of gravity, making them the largest structures in the universe held together by their own gravity. But the galaxies themselves are only the glittering skyscrapers in this cosmic city. What truly defines the cluster is the atmosphere that surrounds it, a vast, seething halo of gas known as the intracluster medium. This gas is heated to staggering temperatures of tens of millions of degrees, so hot that it glows not in visible light, but in a fierce, high-energy X-ray blaze. When X-ray telescopes finally turned their gaze to these clusters, they revealed these halos as colossal, shimmering clouds of immense power and scale. The sheer amount of ordinary matter locked within this intracluster medium is almost unimaginable. In many clusters, the mass of this hot gas alone outweighs all the stars in all the thousands of galaxies within it combined. It is a monumental reservoir of baryons. For a time, this discovery seemed like a major breakthrough in the case of the missing matter. Yet this intracluster medium, for all its staggering mass, was never truly missing. Astronomers had detected it and included it in their cosmic census. It was a known quantity, a vast but accounted-for stockpile of ordinary matter. The real revelation was understanding the role these clusters play in the larger cosmic web. They are not isolated islands, but the most dense and visible knots in a much larger structure. They are the bright, obvious tips of a submerged iceberg. The true, hidden bulk of the missing matter does not lie in these brilliant cities, but in the dark, sprawling country that connects them. This understanding shifted the entire investigation, forcing scientists to ask a new and crucial question. If gravity pulls matter into these dense clusters, what are the specific, violent mechanisms that prevent all the gas from falling in, and instead fling it out to heat and populate the vast, invisible filaments between them? Gravity itself provides the brutal engine for this cosmic heating. The entire cosmic web is in constant, slow motion, a billion-year migration driven by the relentless pull of dark matter. Vast rivers of primordial gas stream from the empty voids toward the dense filaments and clusters, gaining immense speed on their long fall. But this journey does not end quietly. When these colossal flows of matter slam into the already crowded filaments or the outer atmospheres of galaxy clusters, they do not merely merge, they collide. The resulting violence generates immense shock waves, rippling through space and compressing the gas with unimaginable force. This specific process is known as gravitational shock heating. It directly transforms the energy of motion, the gravitational potential energy from the fall, into pure, searing heat. You can experience a small-scale version of this yourself. Take a bicycle pump and place your hand over the metal nozzle. As you rapidly compress the air inside, the pump barrel grows warm to the touch. That warmth is the result of countless air molecules being squeezed together, their energy of motion converted into thermal energy. Now magnify that simple action to a cosmic scale. Instead of a hand pushing a piston, you have the entire mass of a supercluster pulling on rivers of gas. Instead of a pump barrel, you have the vast corridors of space itself. The shock waves generated are not just warm, they are cataclysmic, heating the gas to temperatures of millions of degrees in an instant. This is the final piece of the camouflage puzzle. This incredible heat is what strips the atoms bare, tearing electrons from their nuclei and creating the ionized plasma that is completely invisible to our eyes. The missing matter was never cold and dark. It was the opposite, a seething, luminous ocean of energy, its very brightness tuned to a frequency we were blind to for so long. This crucial understanding directly connects the grand architecture of the cosmic web to the physical state of the atoms within it. The invisible hand of gravity not only builds the universe's structure, but also dictates how we are able to see it. This combination of extreme heat and near-nothingness creates the ultimate observational challenge. The gas of the warm, hot intergalactic medium is so diffuse that a single cubic meter of it might hold only a few hundred atoms. To understand that emptiness, picture the air in your room. That same cubic meter of Earth's atmosphere contains more than 25 quintillion atoms, a number so vast it is almost meaningless. Yet in the cosmic filaments you have a near-perfect vacuum, an emptiness that defies human experience. But here is the paradox. Each one of those few, lonely atoms is a frenzied particle, superheated to millions of degrees and moving at staggering speeds. This duality is the core of the problem. The gas is asked to emit a signal, but there is almost nothing there to emit it. and what little emission it manages is spread over such immense volumes of space that the resulting signal is unimaginably faint. It is the equivalent of trying to detect the heat from a single candle placed on the surface of the moon. For decades, this faint whisper was completely drowned out by the cosmic noise, the brilliant glare from quasars, galaxies, and every other luminous object in the universe. Our telescopes were simply not sensitive enough to isolate this specific, feeble signature. Cracking this case required more than just a new telescope. It demanded a new way of seeing. Astronomers had to become cosmic statisticians, developing techniques to combine the faint traces from thousands of different lines of sight. They were not looking for a single, clear signal, but for a consistent pattern, a faint statistical glow that could only emerge from painstakingly mapping the sky. This monumental effort pushed our technology to its absolute limits, setting the stage for a new generation of observatories designed not to look at the bright objects in the cosmos, but to finally listen for the whisper in the void. The hunt for this faint, cosmic whisper demanded a new kind of eye, one capable of seeing the universe in the searing light of X-rays. For this monumental task, scientists turned to two flagship observatories, orbiting high above the obscuring veil of our atmosphere. The European Space Agency's XMM-Newton and NASA Chandra X-ray Observatory became the premier hunters in the high-energy sky. Though both were designed to see X-rays, they were built with complementary, almost perfectly paired strengths. XMM-Newton is a photon collector of immense power. Its design features nested sets of mirrors, giving it the largest effective area of any X-ray telescope ever built. This makes it exceptionally sensitive to faint, diffuse sources of emission, perfect for gathering the scant X-ray whispers from the vast, hot filaments of the cosmic web. Its specialty is spectroscopy, breaking that faint collected light into a detailed rainbow to read the chemical fingerprints of the invisible gas. Chandra, on the other hand, is the master of sharpness. It provides exquisitely high angular resolution, allowing it to see the fine details within brilliant X-ray sources. Where XMM-Newton gathers as much light as possible, Chandra focuses on creating a perfectly crisp image, like a cosmic scalpel pinpointing the precise location of energetic events. Together, they formed an unbeatable team. To find the warm, hot intergalactic medium, astronomers used these telescopes in their most challenging mode, the deep field observation. They would pick a promising patch of sky, a region where the cosmic web's filaments were predicted to lie, and then they would stare. They pointed these multi-billion-dollar instruments at what appeared to be nothing, at the empty spaces between the glittering galaxies, and they waited. For days, sometimes for weeks, the telescopes would patiently accumulate individual X-ray photons, each one a precious piece of evidence arriving from a journey of billions of years. Slowly, painstakingly, a picture began to emerge from the statistical noise. A faint, diffuse glow materialized, tracing the very filaments that theories had predicted. It was not a bright, obvious image, but a ghostly contour map of heat, a direct detection of the universe's hidden skeleton. These missions turned the theoretical framework of the cosmic web from a compelling model into an observed physical reality. They proved we could finally see the unseeable, setting the stage for a new generation of telescopes designed to map this hidden ocean in its entirety. The eROSITA X-ray telescope transformed this patient search into a grand panoramic census. Launched in 2019, its mission was to perform the first complete all-sky survey in the medium-energy X-ray band, creating a map of the entire hot universe. Unlike the deep, narrow stares of its predecessors, eROSITA scanned the whole sky again and again, methodically building up a picture of cosmic heat emission over the course of 4 years. The result was a revelation, a catalogue of millions of X-ray sources, from nearby stars to the most distant quasars. But its most profound discovery lay in the background, in the faint, diffuse glow between all these brilliant points. Imagine the difference between shining a single, powerful spotlight into a dark alley and turning on the city's entire street lighting grid for the first time. Suddenly, every hidden structure, every forgotten pathway is bathed in light. eROSITA did exactly that for the cosmos, illuminating the vast, dark alleys between the galactic cities. Its true power, however, lay not just in seeing individual filaments, but in its immense statistical capability. Astronomers could now take the data from thousands of pairs of galaxies known to be connected by the cosmic web. They stacked or combined the X-ray signals from the spaces between these pairs. What was an imperceptible whisper for any single pair became a clear, confident shout when averaged across thousands. This statistical amplification finally provided undeniable proof. The faint X-ray glow was real, it was pervasive, and it traced the predicted filaments with stunning clarity. This was the monumental confirmation the scientific community had sought for decades. A large fraction, perhaps even the final portion, of the universe's missing ordinary matter was conclusively located, not in the bright clusters, but in these tenuous, superheated threads of the warm, hot intergalactic medium. With its grand architecture now mapped, the focus could shift from finding the hidden ocean to studying the unique chemistry of its waters. The final, irrefutable evidence came not from the gas itself, but from the unique atomic signatures it left behind. To prove the warm, hot intergalactic medium was real, scientists needed to identify the specific elements within it, and the prime suspect became oxygen. This common element, forged in the hearts of stars and scattered by supernova explosions, is relatively abundant throughout the cosmos. But in the searing heat of the WHIM, oxygen atoms are violently transformed. They are stripped of most of their electrons, becoming highly charged ions known as O7 and O8. This brutal state is their downfall, forensically speaking. An O7 ion, which is an oxygen atom missing 7 of its 8 electrons, has a very specific appetite. It is tuned to absorb X-ray light at one exact, precise wavelength. The same is true for O8. This creates a unique atomic barcode, a set of spectral lines that act as a definitive fingerprint for the presence of this superheated gas. The hunt then became a painstaking exercise in cosmic forensics. Astronomers would take the exquisite X-ray spectra gathered by telescopes like XMM Newton, the detailed rainbows of light from distant quasars, and they would comb through them line by line, searching for those specific, faint dips in the data. Finding these absorption lines was the ultimate confirmation. It was the equivalent of a detective discovering a specific brand of cigarette at a crime scene. You have the location, you have the suspect, but this piece of evidence ties them together beyond any reasonable doubt. These detections did far more than just prove the gas existed. The depth and shape of the absorption lines revealed the gas's temperature, with different ions forming at different heats. The width of the lines hinted at its density and motion. Each successful detection was not just a point on a map, it was a full data packet, providing a crucial measurement for the cosmic inventory. After decades of searching, the case was finally being closed, not with a single dramatic discovery, but with the slow, meticulous accumulation of these atomic fingerprints. The question then shifted from whether the matter was there to just how much of it these signatures were revealing. So did these ghostly filaments finally balance the cosmic books? The answer is a resounding and monumental yes. By carefully weighing the evidence from eROSITA panoramic maps and the forensic absorption line data, astronomers have tallied the contents of the warm, hot intergalactic medium. The numbers are staggering. This diffuse, superheated gas locked within the cosmic web's filaments appears to contain roughly 30 to 40% of all the ordinary matter in the universe. When you add this to the mass already accounted for in stars, galaxies, and the brilliant intracluster gas, the total finally matches the pristine prediction from the Big Bang. The missing matter has been found. This successful accounting is one of the greatest triumphs in modern science, closing a chapter that puzzled astronomers for decades. The matter never truly vanished. It was always there, a hidden ocean surrounding the islands of light we could see. Its camouflage so perfect it took our most advanced technology to finally perceive it. With the mystery of its location solved, a new and even more profound question emerges. This vast reservoir is not a static pool. It is the fuel for the future and the graveyard of the past, a crucial part of the great cosmic cycle of matter. How does this immense volume of hot gas actually influence the birth and death of the galaxies it connects? This discovery redefines the very nature of cosmic emptiness. The spaces between galaxies are not a graveyard for matter, but a dynamic, churning hub in a continuous cycle of creation and destruction. This is the cosmic cycle of baryons, a grand recycling process where ordinary matter flows between different states, never truly disappearing, only changing its form. It begins within the bright disks of galaxies, where cool, dense clouds of gas collapse under their own gravity to ignite new stars. These stars live spectacular lives and die in even more spectacular supernova explosions. These stellar deaths are not merely an end, they are a powerful new beginning. The blasts eject colossal amounts of enriched material, heavy elements like oxygen and iron forged in the stellar furnace, back into space. This material does not just float gently away, it is hurled out by immense galactic winds, torrents of energy driven by the combined force of countless supernova, or by the furious activity of supermassive black holes at the galaxy's core. These outflows act like cosmic fire hoses, spraying gas and newly forged elements far out into the intergalactic medium, seeding the void with the very ingredients for future planets and life. This is the outflow, the galaxy's way of exhaling its processed material back into the cosmic reservoir. But for a galaxy to continue forming stars, it cannot only exhale, it must also inhale. This is the other half of the cycle, the inflow. Vast rivers of pristine, cooler gas from the cosmic web continually rain down upon galaxies, drawn in by the relentless pull of gravity. This fresh fuel, which has not yet been locked up in stars, is the essential raw material that replenishes a galaxy's star-forming reservoirs. The warm, hot intergalactic medium is the central player in this entire ecosystem. It acts as a massive holding tank, a temporary home for matter between its galactic incarnations. The gas ejected from galaxies joins this reservoir, where it is heated and diluted, and the gas that flows back into galaxies is drawn from this same vast pool. Think of a great ocean that evaporates to form clouds, which then rain down to feed rivers that eventually flow back into the ocean. The WHIM is that ocean, the fundamental reservoir in the universe's water cycle. This means the so-called missing matter was never truly lost. It was simply in transit, a vital part of a circulating system that governs the growth and evolution of every galaxy we see. Without this constant exchange, galaxies would rapidly consume their available gas, star formation would sputter and halt, and the universe would become a much darker, quieter place. The discovery of the WHIM and its role in this cycle forces us to ask a final, profound question about our own place in this cosmic flow. This discovery fundamentally rewrites the story of a galaxy's life. We can no longer view galaxies as isolated islands growing in splendid solitude. They are deeply embedded in and regulated by their environment, connected to a vast circulatory system of hot gas. The presence of this massive reservoir in the cosmic web solves a critical problem in galaxy formation, the mystery of long-term fuel supply. For a galaxy to keep forming stars for billions of years, it needs a continuous source of fresh, cool gas. The warm, hot intergalactic medium provides this essential reservoir. Galaxies can slowly accrete or draw in material from these surrounding filaments over immense timescales, a steady trickle of fuel that governs their star formation rates and ultimately determines their final sizes and masses. This process is not always gentle. Think of a galaxy moving through a dense filament like a car driving through a light rain. The galaxy's own motion and gravity funnel the gas inward, but that gas is still incredibly hot. As it gets pulled into the galaxy's halo, it must radiate away its immense heat, cool down, and condense before it can ever collapse to form new stars. This delicate balance between accretion and cooling is the true regulator of a galaxy's vitality. Without this external fuel source, a typical galaxy would exhaust its internal gas reserves in a cosmic blink, its star formation ceasing in just a few 100 million years. The hidden ocean of the WHIM is what allows the bright islands of stars to shine for eons. This new understanding has a direct and powerful impact on the supercomputers that simulate our universe. For decades, the most sophisticated models of cosmic evolution had a glaring hole in their equations, a forced fudge factor to account for the mass they knew was there but could not locate. Now, with the Baryon budget finally balanced, these simulations can run with a complete and accurate set of ingredients. The result is a stunning increase in predictive power. Virtual universes generated in supercomputers now more closely resemble the real cosmos we observe, with galaxies forming in the right places at the right times and growing to the correct sizes. This success powerfully validates the hierarchical model of galaxy formation, the leading theory that the universe builds from the bottom up. In this model, small proto-galaxies form first within the dark matter web. They then merge together and, crucially, continuously draw in fresh gas from the cosmic filaments, gradually assembling into the majestic spirals and ellipticals we see today. The discovery of the WHIM confirms that this gas supply line is not just a theoretical idea, it is a physical reality. Our maps of the cosmos are no longer just of the stars, but of the rivers that feed them. With this fundamental piece of the puzzle now firmly in place, our gaze turns outward to the next great frontier, the very dawn of galactic time. But for all our success, our map of this hidden ocean remains frustratingly blurry. Today's X-ray telescopes have reached the absolute limits of their vision, pushing against a fundamental barrier of faintness. While we can confirm the existence of the warm-hot intergalactic medium through statistical stacking and spot its brightest strands near colossal galaxy clusters, we still cannot see the vast majority of its individual, wispy filaments in clear detail. The signal from a single, isolated thread of this gas is simply too weak for our current instruments to pick out from the cosmic background noise. It is the difference between knowing a vast mountain range exists because you can see its silhouette against the horizon, and being able to trace every single footpath, stream, and rock formation that covers its slopes. We have the outline of the continent, but the intricate geography within remains a mystery, hidden in a pervasive, low-resolution haze. This limitation is more than just an observational annoyance. It is the primary obstacle to understanding the true nature of this cosmic ecosystem. We know the gas is there, but we cannot yet study its intricate physics. How does it swirl and churn? Do magnetic fields thread through these filaments, shaping their flow? How are the heavy elements from ancient supernova mixed and distributed throughout this vast reservoir? These are the critical questions that remain just beyond our grasp, locked inside a whisper we can hear but cannot yet fully decipher. The very success of finding the missing matter has now illuminated the next great frontier, revealing just how much we still have to learn about the dynamics of the invisible universe. Our current tools have brought us to the shore of this hidden ocean, but to explore its depths, we will need to build a new kind of ship. That final leap in vision requires a new kind of telescope, one designed not just to see the hidden ocean, but to sail upon it. The future of this exploration rests with a revolutionary mission known as Athena, the Advanced Telescope for High-Energy Astrophysics. Planned by the European Space Agency for a launch in the mid-2030s, Athena is not merely an upgrade, it is a complete transformation of our X-ray vision. Its design combines two previously incompatible powers on an unprecedented scale. First, it will possess a colossal collecting area, a giant eye capable of gathering X-ray photons with an efficiency far beyond any current instrument. Second, and just as crucially, it will wield an exquisite high-resolution spectrometer, a device that can split the collected light into a rainbow of breathtaking detail. This powerful combination will shatter the current observational barriers, where today we must combine thousands of faint signals to get a single, blurry reading. Athena will be able to point at a single, wispy filament of the warm, hot intergalactic medium and perform a detailed diagnostic check. It will measure the gas's temperature with precision, trace its density variations along the filament's length, and even clock its velocity, revealing how this material is flowing toward or away from galaxies. Athena will transform the WHIM from a statistical ghost, a faint glow we can only see in the average, into a rich collection of individual objects, each with its own story to tell. This is the shift from knowing a forest exists to being able to study the biology of every single tree within it. The mission promises to turn the final page on the missing Baryon problem, not by simply confirming the matter's presence, but by revealing its intricate life cycle in stunning, dynamic detail. This coming leap in capability is already fueling a surge of theoretical work, as scientists prepare models and predictions for the torrent of new data that will soon redefine our place in the cosmic web. These digital universes are not video games, but some of the most ambitious scientific experiments ever conceived. Inside the world's most powerful supercomputers, cosmologists build entire cosmos from scratch, starting with the initial conditions of the Big Bang and then letting the laws of physics take over. Projects with names like Illustris TNG and Eagle simulate the evolution of billions, even trillions, of particles representing both dark matter and ordinary baryonic matter. They watch as gravity sculpts these particles into a cosmic web over billions of simulated years, a process that would be impossible to witness in real time. And crucially, these simulations did not just stumble upon the warm, hot intergalactic medium. They actively predicted it, long before our telescopes had the power to see it. These digital laboratories told scientists exactly where to look and what to look for. They forecast that a vast, hot web of gas would form in the filaments, and they even predicted its temperature range and density. This was not a lucky guess. It was a direct consequence of programming the known laws of gravity, hydrodynamics, and gas physics into the simulation, and letting the virtual universe run its course. How do you test a theory about a process that takes billions of years? You build a universe where you can fast forward through eternity. These models became the ultimate guidebook for observers, providing a treasure map to the missing matter. When the first faint X-ray signals from eROSITA began to match the simulated maps filament for filament, it was a moment of profound validation. The real universe was behaving exactly as the digital one said it should. This synergy is the engine of modern discovery. The simulations make a prediction, the telescopes go out and test it, and the resulting data is then fed back to refine and improve the models. It is a continuous cycle of questioning and verification that steadily sharpens our picture of reality. These digital laboratories also allow scientists to run experiments that are impossible in the real cosmos. They can effectively turn off certain forces, like the explosive feedback from supernova, to see what happens. In simulations without this galactic wind, far too many stars form, creating galaxies that look nothing like the ones we see. This virtual tinkering proves that the violent outflows from galaxies are not just a side effect. They are essential for regulating star formation, and just as importantly, for pumping energy and enriched gas out into the intergalactic medium, helping to create and sustain the warm-hot intergalactic medium itself. The simulation becomes a time machine, letting us rewind the tape of cosmic history to understand not just where the missing matter is, but how it got there in the first place. With our cosmic inventory nearly complete and our theoretical models proven robust, a deeper question begins to surface. What does the existence of this vast, hidden ocean mean for the ultimate fate of all the structures within it? This crucial distinction often gets blurred in the grand story of cosmic missing matter. The hunt we have been following, the search for the vanished baryons, is entirely separate from the deeper and far more mysterious puzzle of dark matter. They are two different cases on the same cosmic detective's desk. The baryons, the ordinary matter we have been tracking, are made of the same stuff as you and me. They are protons, neutrons, and electrons, the building blocks of atoms that form every star, planet, and person. This matter interacts with light. It can absorb light, emit light, and reflect light, which is precisely why, in principle, we were always able to find it. Our challenge was not that it was fundamentally invisible, but that it was hiding in a state that made it incredibly difficult to see. Dark matter, on the other hand, is something else entirely. It is a different substance, an unknown form of matter that does not interact with light at all. It does not glow, it does not cast a shadow, and it does not block the light from distant stars. As far as we can tell, it passes through normal matter like a ghost walking through a wall. Its presence felt only through a single, powerful force, gravity. The dark matter's gravitational pull is what guides the formation of the cosmic web, sculpting the vast filaments where the hot baryonic gas eventually resides. Think of it like a puppet master and the puppets. Dark matter is the unseen master, pulling the strings of gravity that dictate the cosmic performance. The ordinary baryonic matter is the puppet, the visible actor that follows the stage directions, glowing and moving for all to see. The scale of this division is staggering. The successful accounting of the missing baryons, the culmination of decades of work, only solves the case for the ordinary matter, which makes up a mere 15% of the total matter in the universe. Dark matter constitutes the other 85%. It is the dominant component of the cosmic mass, the true unseen bulk of existence. Finding the missing baryons does not bring us any closer to identifying the nature of dark matter, but it does something just as important. It cleans up the cosmic ledger, allowing us to isolate the dark matter problem with perfect clarity. We now know exactly what belongs to the ordinary world and what remains in the realm of the truly unknown. This separation is fundamental. It means that when we look out at the grand architecture of the cosmos, we can now distinguish the luminous threads of the hot gas we have found from the dark, gravitational skeleton that holds it all together. Our map is finally complete for one layer of reality, revealing just how much deeper the true mystery goes. This discovery forces a profound shift in our cosmic perspective. The world we experience with our own senses, the solid ground beneath our feet and the brilliant stars overhead, represents only a tiny sliver of even the ordinary atomic universe. The majority of this familiar matter is not here with us. It exists as a seething, invisible ocean, a hot fog permeating the immense voids between the galactic islands. We are surrounded by a reality that is fundamentally beyond our biological perception, a realm we can only access through the extended senses of our technology and the power of our reason. This is a deeply humbling thought. Our entire evolutionary history has tuned us to perceive a world of medium-sized objects moving at medium speeds, a reality of solid surfaces and immediate dangers. Yet the true nature of the cosmos is one of extreme emptiness and violent, invisible energies. The very atoms that make up our bodies are the same ones that are currently superheated to millions of degrees in a distant filament of the cosmic web. We are not just looking out at the universe from a detached vantage point. We are of it, intimately connected to a hidden circulatory system whose existence we have only just proven. This achievement stands as a powerful testament to human curiosity. We have used the consistent laws of physics, tested here on Earth, to deduce the existence and properties of a substance we can never see, touch, or smell. We have built tools that can read the faint shadows this hidden ocean casts upon the light of quasars and the echo of the Big Bang. In doing so, we have dramatically expanded our conception of what is real. Reality is no longer just what we can directly experience. It is also the vast, hot, dark web that our intellect and ingenuity have revealed, connecting the atoms in our hands to the grandest structures in the cosmos. This monumental discovery, once confined to scientific papers, now needs to be shared with its true owners, everyone. The challenge is making an invisible, superheated ocean of gas feel real and tangible to a public that rightly wonders what it all means. The solution has been a powerful fusion of science and art, using breathtaking visualizations born from supercomputer simulations. These are not mere animations, they are data-driven portraits of the cosmos, transforming trillions of calculations into a fly-through of the shimmering cosmic web. You can watch galaxies form at the intersections of glowing filaments and see the warm, hot intergalactic medium represented as a faint, ethereal glow along the dark threads. In planetarium domes around the world, audiences are enveloped by these visuals, taking a journey through a universe that was pure theory just a generation ago. Documentaries weave these simulations into their narratives, turning abstract concepts into a grand, visual story. Interactive websites allow anyone to zoom in from the scale of the entire observable universe down to a single galactic cluster, exploring the connections for themselves. This process of visualization does more than just inform, it demystifies. It takes cutting-edge astrophysics out of the ivory tower and places it directly into the public imagination, proving that these are not impossibly complex ideas but solvable puzzles. For a young student seeing that cosmic web for the first time, the message is clear. The universe is not a closed book. Its greatest secrets are waiting to be uncovered, not by magic, but by the persistent application of human curiosity and ingenuity. By making the public a partner in this discovery, we foster a deeper appreciation for the fundamental science that explains our place in the cosmos and for the incredible technological marvels, from space telescopes to supercomputers, that make such insight possible. Sharing this story is not the end of the journey. It is an essential part of the ongoing exploration, inviting everyone to look up and wonder what we will reveal next. With the mystery of the missing matter now solved, a few stubborn myths still linger in the cosmic shadows, clouding the true brilliance of this discovery. One of the most persistent ideas is that this matter was somehow annihilated or vanished into another dimension. The reality is far less magical and far more grounded in physics. The atoms were never destroyed. They were simply wearing a perfect camouflage, existing in a superheated, ionized state that rendered them invisible to the eyes we had trained on the universe for centuries. Think of a master spy who can walk through a crowded street completely unseen, not by turning invisible, but by blending in so perfectly that no one thinks to look twice. The matter was always there, we just needed to learn how to see it. Another common confusion lumps the missing baryons together with the deep enigma of dark matter. It is crucial to understand they are two entirely separate puzzles. The baryons are the ordinary atoms, the stuff of stars and planets and life itself. We found them by finally detecting their faint, high-energy whisper. Dark matter, by contrast, is something else entirely, a substance that does not interact with light at all. Its presence is felt only through its immense gravitational pull, which sculpts the cosmic web itself. Imagine you are watching a play in a vast, dark theater. The ordinary matter is the actor on the stage, now fully illuminated by our X-ray spotlights. Dark matter is the unseen stagehand moving the sets and pulling the ropes in the darkness behind the scenes. We have finally found the actor, but the stagehand remains a complete mystery. This leads to a third misconception: the idea that the space between galaxies is a true and perfect void. Nothing could be further from the truth. The cosmic voids are indeed the emptiest places we know, but the filaments of the cosmic web that weave through them are filled with the warm, hot intergalactic medium. It is a ghostly ocean, so diffuse that its contents would qualify as an excellent laboratory vacuum on Earth, yet so vast that it holds nearly half of all normal matter. The emptiness of space is an illusion of our limited perception. We now know that if you could see in X-ray vision, the sky would not be a dark blanket punctuated by stars, but a shimmering, intricate web of faint, hot light, a hidden architecture connecting all things. The story of the missing matter is not one of loss, but one of revelation. We did not recover something that was gone. We simply learned to read the universe in a new language, using tools that could finally hear its faintest whispers. Solving this cosmic mystery demanded more than just a bigger telescope. It required a symphony of human knowledge, a convergence of disciplines that had to learn to speak the same language. Fundamental physics provided the first essential notes. Scientists had to understand the bizarre behavior of matter in its plasma state, predicting how atoms like oxygen would be stripped of their electrons and what specific X-ray light they would absorb. Without this deep knowledge of atomic transitions, the faint fingerprints in the quasar spectra would have been meaningless hieroglyphics. Then came the monumental task of engineering. Designing and building instruments like the Chandra and XMM Newton telescopes pushed the limits of material science and precision manufacturing. Their nested mirrors, capable of grazing incoming X-rays into a focus, are feats of engineering that operate in the harsh environment of space, a testament to human ingenuity. Once the data started streaming down, the challenge shifted to computation. The faint, statistical signal of the warm, hot intergalactic medium was buried in a sea of noise. Computer scientists and statisticians developed sophisticated algorithms to clean the data, stack thousands of observations, and perform the complex calculations that would tease a coherent signal from the cosmic static. This was not a linear process, it was a constant, global conversation. Physicists talked to engineers about what was possible to build. Data scientists worked with astronomers to interpret the strange patterns emerging from their code. The supercomputer simulations which guided the entire search were themselves a product of this collaboration, blending cosmology, fluid dynamics, and computer science into a single digital laboratory. This breakdown of traditional silos is the new blueprint for discovery. the most profound questions about our universe can no longer be answered by a single field working in isolation. They demand a collective effort, a shared toolkit drawn from every corner of science. This successful model, forged in the hunt for missing atoms, is now our best hope for confronting the next, even deeper enigmas. The nature of dark energy, the force accelerating the universe's expansion, awaits its own interdisciplinary symphony, a puzzle that will likely require us to invent entirely new ways of seeing once again. The case of the missing matter is officially closed, but the story of the cosmic web is just beginning. Our focus now pivots from a grand treasure hunt to an intimate examination of the treasure itself. We know the warm, hot intergalactic medium is there, a vast ocean of hot gas. The new, more intricate questions are about its currents and tides. How exactly does this gas churn and flow within the delicate filaments? Is it a smooth, steady river or a turbulent, chaotic cascade? We need to understand the intricate physics of how energy and heavy elements are mixed and transported across these immense cosmic highways. This leads directly to the powerful influence of galactic feedback. Supermassive black holes and supernova explosions act as cosmic engines, blasting winds of energy and material out into the void. But what is the precise impact of these titanic eruptions on the properties of the WHIM? Do they simply heat the gas, or do they also seed it with the specific elements necessary for future planets and life? Perhaps most fundamentally, we must ask how this ordinary, seething plasma interacts with the dark matter that holds its home in place. Dark matter's gravity sculpts the cosmic web, but does the heated baryonic gas push back in any way, influencing the very structure it resides within? Answering these questions requires a leap in vision, one that will be provided by the next generation of observatories. The upcoming Athena mission, along with other powerful telescopes, is designed to do more than just detect the WHIM. It will study it as a dynamic and complex ecosystem. These instruments will measure the gas density, temperature, and velocity along individual filaments, transforming them from blurry statistical blobs into detailed, three-dimensional structures we can explore. The solution to one great cosmic riddle has not ended our quest. It has flung open a door to a new and even more fascinating chapter, where the hidden architecture of the universe becomes a living, breathing character in its own epic story. Our cosmic ledger is finally balanced. The journey to find the missing matter stands as one of modern astronomy's greatest triumphs, a story that began with a glaring deficit in our inventory of the universe and ended with the discovery of a hidden ocean. We now know the atoms did not vanish. They were simply cloaked in a state of perfect invisibility, a superheated plasma woven through the filaments of the cosmic web, undetectable to the eyes we had trained on the sky for centuries. This ghostly medium revealed itself only through the subtlest of signatures, the faint absorption of X-ray light from distant quasars, and the slight distortion it imprinted on the ancient afterglow of the Big Bang. It took a new generation of space-based observatories with their ability to see the high-energy universe to finally illuminate this dark architecture. This discovery does more than just fill a gap in a cosmic spreadsheet. It powerfully validates the entire framework of our cosmology, confirming that our theories of the Big Bang and the growth of cosmic structure are fundamentally correct. The universe has been playing by the rules all along. We just needed to learn how to read its hidden language. It is a testament to our relentless drive to explore, to push beyond the limits of our senses and build tools that can see the unseeable. We have shone a light into the darkest corners of existence and found not emptiness but a vibrant, dynamic structure that connects all things. This is not the end of the story, but a new beginning. As we stand on the shore of this vast, hidden ocean, we can only wonder what other secrets the cosmos holds. waiting for the next curious mind to ask the right question and reveal another layer